From the PowerPoint, you're going to see a slide. It's called Descartes' Rule of Signs, and it tells us how do we figure out the number of positive real zeros and negative real zeros. So for positive real zeros, we're looking for sign changes of f of x. That means if we use the original equation as is, we see how many changes there are in the coefficients. Well, we're going from 2 to 8 to 51 to 72 to 135. They're all positive. So therefore, there are no sign changes of f of x. So therefore, there are 0 positive real zeros. Now remember, we alternate by taking away, well, we'll say that in a second. In other words, that if we have imaginary answers, those always in powers of 2. So we have to keep that in mind. So for negative real zeros, we're looking at sign changes for f of negative x. So looking at this problem here, we put in negative x, and what do we have? Well, we're going to have a positive there for our coefficient. We're going to have a negative next, because a negative to the third power is going to be negative. We're going to have a positive there. We're going to have a negative there, and we're going to have a positive here. So look at the number of sign changes. We have 1, 2, 3, 4. So it looks like we have 4 negative real zeros. But if it were only 2, let's just say, that means we could have 2 imaginary ones at also. But the fourth power is the highest power in this problem, so that's the most number of real zeros there could be. It doesn't mean there's guaranteed to be, because we could have some imaginary and some real. Okay, well, this problem asks us to use the same Descartes' rule of signs to determine the number of possible negative and real zeros. And all possibilities meaning that we have to include differentials of 2 for imaginary answers. So, looking for positive ones. Well, as is, we go from positive to negative to negative to positive. So we look there, we have 1 sign change, 2 sign changes. So the number of positive real numbers for f of x was 2. So therefore, the number of positive real zeros are 2 or 0, because they could be 2 imaginary answers, and they cannot be real. So that's why we put that. And they're always a differential of 2. That's why there's not a 1. All right, because you can't have one imaginary number by itself. Now we have to look at f of negative x. That means we put negative x in place of regular x, and if that's the case, we're going to get negative there, and a negative squared times a negative, that's also going to be negative. Negative times a positive, sorry, a negative times a negative is a positive, and the last one is positive. So we only have 1 sign change there, if I'm reading that right. So the total number of real answers in this problem is 3. 0 or 2 of them are positive real numbers, and negative real zeros are numbers, zeros. This one is 1, so we definitely have 1 real negative 0. Okay? So therefore we have 1 real 1, and it could be 2 real positives or 0 positives, and therefore it would be 2 imaginaries. Okay, now in this problem we're asked to use the synthetic division to find the upper and lower bounds. Well, that would involve finding the factors of 50 over the factors of 1. So it's really the factors of 50. So in order to, let's plus or minus, so that could be plus or minus 1, 2, 5, 10, 25, and 50. So we're trying to find a number where there's no answers above it. So let's say we first try 5. Okay, if we first try 5 and see if that works. Now, what are we looking for? We're looking for all non-negative numbers at the bottom, synthetic division. Okay, so that means the moment we stop, the moment we get a pattern that ruins that pattern, we could stop right there and go to our next candidate. So we have 5, 1, negative 2, negative 25, and 50. So we'll keep going, and we're looking for all positive or 0. So nothing with a negative number. The first negative number we get, we could stop and go to a higher number. So we try 5. We get 5. It's going to be 5. We add that, we get 3. So we're okay so far because we have or positives or 0. 15. Oh, when we combine that, we get negative 10. So right there, right off the bat, we know 5 is not high enough. So now we go to 10. See if 10 gives us the desired result in synthetic division. So we have 1, negative 2, negative 25, and 50. Okay. So now bring down the 1. And we got 10, we got 8, we got 80, and 55. It's really big, 550. So 550. 550, sorry about that. And that's going to give us 600, so that's definitely positive. Notice there's no negative numbers down there, so 10 is an upper bound, so we got that one. Now we have to look for a lower bound. And a lower bound, we're looking for alternates, okay? All alternating zero can be positive or negative, so once we get two signs in a row, like two positives or two negatives, we stop and we go with something lower. So let's try like -5, for instance. Try something kind of in the middle, so it gives you some, it eliminates some answers below it, right? Because if you go for the lowest number, it's not, a lower bound's not really helping you because you could still have all those answers above it. So let's go here. What do we got? We got 1, -2, -25, and 50. And if we do that, we drop the 1, and we get 5, and we get 3. So automatically we don't have alternate right there. We could stop right there. Well, we know that 1's not low enough. We drop the 1. Oh, it's -5. My bad. I thought that was not right. Okay. So that was -5. That's -7. We combine. Sorry about that. -7, -5 times -7 is 35. We're at 35 there. So 25 and 35 is 10. So we're still alternating. Yes. And then that's -50. So that is 0. And remember, 0 counts as either negative or positive. So that is a switch. That is a switch. And that is a switch because 0 counts either way. So -5, luckily for us, that is a lower bound. Okay, so -5 is a lower bound and 10 should be an upper bound. Okay, a slight addendum to the previous question. We realized that 5 did not work for the upper bound, but 10 did. Now, just because 10 works doesn't mean that that is the highest upper bound. There could be one like 9 could work or 8 could work. So we're not limited to only the factors of 50 in this case, of an in order a0. So in other words, we know that 5 did not work, and we know that 10 did work, but that might not be the upper bound. I mean, 10 is an upper bound, but it's not the lowest upper bound. We want to get the lowest one, so like 9 or 8 or 7 or 6 could work. So what I did here for you is just to show you that you start after 5. What you'll see is that you try 6 and the pattern doesn't work, right? So you try 7, and then you notice when you try 7 that you get all positives. So 10 is an upper bound. There are no answers above 10. That's true. And normally we think of all the factors of 50 as only numbers we could use, but we know that 5 did not work. So somewhere between 5 and 10 is a more accurate or lower upper bound. And so we found out that 7 is the more accurate lower bound for that one. So you'll need to know that for Hawks when you're entering your answers. The previous problem, part 3, asked us to find all the zeros using the following information that we used from part A and part B. Well, we found out when we put in a -5, we found out that it gave us a 0. So when we did that one it was here, we had -5. We found out that we had 0 there. So that means that that -5 is one of the zeros. Well, from that point, we have a quadratic right here. Remember, this is the constant, this is the x, and this is the x squared. So we have x squared minus 7x plus 10 equals 0. If we factor that, we get x minus 2 times x minus 5, and we get x equals 2 and x equals 5. So that means our three answers are -5, 2, and 5. So if we have a third degree, which we did, and once we get 1, 0, once we get down to 2 left, like a quadratic, then we could just solve it without using the synthetic division any longer. So the potential zeros, rational zeros of this problem is going to be the factors of an, which in this case is -4, over the factors of 1, okay? So remember that when we have x cubed minus 4x squared plus x minus 4, this is a0 and this is an. So therefore we're looking for factors of 4 over factors of 1. So you're just going to have plus or minus 1, 2, and 4. And since an is 1, we don't have any fractions here, so it's going to be plus or minus 1, plus or minus 2, or plus or minus 4. All right, now number 2, part 2 of this problem asks us to use polynomial division to find and quadratic formula. Well, we can't use quadratic formula yet because we have a third degree, so we have to change that to a second degree. So we know that it was plus or minus plus or minus 1, it was plus or minus 1, 2, or 4 in the previous problem. So, I mean, if you can kind of eyeball that, you can see that 4 is going to work. If you plug in a 4, you're going to get 64 minus 64 plus 4 minus 4, and that's going to give you 0. Or you can do the upper and lower bound trick as follows. So do whatever you need to do. But for the sake of the purposes of this, I kind of guessing that it's going to be x equals 4. So that's why I put x minus 4 out here as my factor. So if I do that, I'm going to have an x up there, and then I multiply down. I'm going to get x into here. Oh, x into x to the third is x squared. So you multiply x squared down. Okay. And if you do that, you're going to get x to the third minus 4x squared. And if you subtract those, you're going to get 0 here. You bring down, you're going to get 0, 0. You're going to get x minus 4. And then you divide that in there. And it's going to be x to the x minus 4 minus, and to x minus x into x goes in once. Plus, looks like plus 1. X minus 4 goes in here plus 1 time. So you get x minus 4. Subtract, you get 0. So indeed, x minus 4 is a factor, and it goes in. So that means 4 is a factor. And what do you have left? We have x squared plus 1 left. Well, that means I'm going to get I, and negative I. So our three answers are going to be 4, I, and negative I. So using the intermediate value theorem, we have to show that f of 1 and f of 2 are different signs. So we can do that more efficiently with the synthetic division for each one and see what signs they yield. And if they change from positive to negative or negative to positive, then we're going to say yes, there is a solution, because that means that a curve must go over the x-axis. You see one side's positive, one side's negative with their y value. That's the idea, okay? So therefore, we're going to proceed here. We get a 6. Put 6, we get 360. We get 360. And that's what? That's positive 480. That's going to be positive 7, 8, 40. That's going to be 840. So that's going to be positive. It's positive like 356 and 350. So no matter what it is, that's definitely positive. So let's try f of 2 now. Okay. So we're going to try f of 2 now and see if we get a negative result. Okay. Let's clear some space down here. All right. So going back here, now we try a 2. If we try 2, all we care about is whether it's positive or negative. We don't have to get the exact answer. We drop the 6. This is what? This is 354. This was 480. This was negative 486, and this one was negative 90. So we're going to get 12. It's going to be positive 66. That's going to be 720, 732. It's going to be big and positive. So it's 11. That's like 12, 12, 2400, whatever, 2400. So that's going to be positive. Approximately like 1900. So that's going to be way positive. So this is definitely a big positive. Doesn't matter exactly what it is. So there's no real sign change there. So we're going to say no. There's not a 0 between 1 and 2. So to list using the rational zero theorem to see whether or not what all the rational zeros are, it's going to be a0 over an. So it's factors of negative 50 over factors of 1. So that's simply going to be plus or minus, and you're going to have 1, 2, 5, 10, 25, and 50. So that really means 1, 2, 5, 10, 25, and 50, and negative 1, negative 2, negative 5, negative 10, negative 25, and negative 50.